In this video, we're going to continue our exploration of radicals and all of their laws by looking at rational exponents. So when we say rational exponents, we're now talking about exponents where we have either a fraction or some kind of a decimal up there, usually going to be fractions. And you can see our first rule here we're going to explore is a to the 1 over n power. But before we explore the rule, we need to take a look at some guidelines for what type of numbers we're talking about here. So for all these problems in the next few slides, we're going to say that a and also the nth root of a, those have to come out as real numbers. And there's a symbol for real numbers here. They have to be part of this set of real numbers. We're also going to use a lot of letters, m's and n's in this problem. And anytime I refer to m or n, you can assume that those are going to be positive integers. And if you've never seen this before, the letter z in math language refers to integer. So we're only going to be talking about integers here. So a to the 1 over n power is defined as the nth root of a, quite simply. So I can show this through two examples. For example, if I say 64 to the 1/3 power, that means the cube root of 64. And 64 happens to be one of these numbers that I know the cube root for. There aren't many, but I know that the cube root of 64 is 4. So 64 to the 1/3 power is 4. How about if we try a negative? What if I say negative 32 to the 1/5 power? Well, in this case, I have negative 32, and I want to do the 5th root of it. And you recall from the last section that I can do the odd root of a negative number. That's possible. And 32, I know that the 5th root of that is 2, so this will come out as negative 2. So fairly easy rule, a to the 1 over n power just means the nth root of a. Continuing on, what if I have a to the m over n power? There's actually a couple different ways to express this. I'm going to show you 4 different ways, and I'll show you how we can use them in problems. One way to say this is it's a to the 1 over n power raised to the nth power. And if you think about what we know about exponents, this is valid because when we have a power to a power, we multiply those guys and we would have m over n. So that's one way to express it. Another way to express it is, what if I took a to the m power and then raised that to the 1/n power? That would also be another way of looking at it. If I wanted to simplify them as radicals, this also means that I could take the nth root of a to the m power. That would be another way of thinking of it. Or another way yet would be, what if I did the nth root of a first and then took that answer and raised it to the nth power? So in these problems, you do have a lot of options here. There's a couple ways you can write the same thing. And I'll give you a couple examples here where you kind of see what the best way to go about this is. So let's say, what if I had 125 to the 2/3 power? And I'm going to go ahead and write this directly as my radicals in these last 2 examples. Look at it these ways, because I want to try to simplify this guy. So there's 2 ways to look at it. I could look at it as the cube root of 125 squared, or I could look at it as the cube root of 125 and then that answer squared. And I have to make a decision as to which one of these is going to be more efficient for me. And you look at their differences. Well, this first one says I have to take 125 and square it. That doesn't sound like a whole lot of fun to me. So I'm really looking at this one, because this one I can do fairly easily in my head. I know what the cube root of 125 is, and I can square that. Well, I know that the cube root of 125 is 5, and I'm going to square that answer, and that comes out as 25. So 125 to the 2/3 power is 25. Another one, what if I took negative 4 to the 5/2 power? Now, to be careful here, not to be careful how I say this, this actually reads as the opposite of 4 to the 5/2 power. It's really 4 to the 5/2 power. Whatever answer I get, I'm going to take the opposite. Note that this is not the same as negative 4 to the 5/2 power. And that would be a common mistake here. So this is not what I want. What I need to do is 4 to the 5/2 power, and then I will take the opposite of its answer. So I'll bring the work down here. So how do I want to write this? Well, I know that I'm taking 4. I know that I'm going to take the square root of it. And somewhere I'm going to do the 5th power. I could either do it here, or I could do it like this, where I take the square root of 4, and I raise that to the 5th power. And again, I think you'll usually find that this second option is going to be the most desirable, because I have a square root here. I know how to do that. The square root of 4 is a number I know. That's 2. I can raise that to the 5th power. That's 32. So I have an answer of 32, but I do have to remember this pesky opposite sign here. My answer is negative 32. Okay. All right. Moving on. More rules. What if I have a to the negative m over n power? Well, this is just an extension of what we did before. The way this is defined is, remember what a negative exponent does. It really just does the reciprocal. So this is the same as 1 over, 1 over a to the m over n power. Okay. And one thing I have to remember here, this means that a cannot equal 0. I have to be careful of that situation here. We'll put that little restriction on it. So one example of this, what if I tried to do 16 to the negative 3/4 power? That would be the same as 1 over 16 to the 3/4 power, which is the same as 1 over, again, I want to do the 4th root of 16, and I will cube that answer. 4th root of 16 is a number I know. It's 2. So this is 1 over 2 cubed, and then I have 1/8. So just an extension of what we had already. We just have to remember that we can do a reciprocal there. Okay. So what comes up from here is we really need to look at the laws of exponents that we learned in Algebra 1 and revisit them. But this time we're allowed to have some rational numbers here. So we're going to look at all the laws of exponents very quickly here. But keep in mind here, we are going to let R and S, they're going to be in the set of rational numbers, rationals. And you also see we have some A's and B's here. We want A and B to be real numbers, any real numbers. So these are the restrictions for which these rules hold. And right now they're not a big deal, but eventually we'll get to some that are a little bit nastier. So you just need to recall your rules here. This first one, anytime we're multiplying two expressions, it means we add their exponents. It's the same as A to the R plus S power. Same stuff we did in Algebra 1. Keep in mind, in this one, anytime that we are dividing with the same basis, it means we subtract our exponents. So this is A to the R minus S power. In the third situation here, we're allowed to take the R and apply it to both of the problems, both of the expressions within the parentheses. So this is A to the R times B to the R. Okay. I'm actually going to skip around a little bit. I'm going to skip the fourth one here and come back up to the top here. What if I had A to the negative R power? That's the same as 1 over A to the R. Another one that comes up is a power to a power problem. In that case, we're allowed to multiply A to the R times S. And in this one, just like in the earlier problem where we are allowed to apply the R to both things in the parentheses, we have the same thing here. This is A to the R over B to the R. And finally, I saved this one for last because we have that nasty negative here. This means that we're going to do the reciprocal and raise both to the R power. So if I take the reciprocal, this is the same as B over A to the R power, and that means B to the R over A to the R. And I'm going through these rules rather quickly because there's really nothing new here. These are the same rules you had in Algebra 1. Just know that we can now apply them with our rational expressions as well. So to end this video, I have two examples, and they look fairly nasty here. But if you think about our rules, we're going to use our rules to try to make some sense of them. We're going to try to simplify them as much as possible. And for the most part, simplifying will mean that we don't want any negative exponents when we're done. So we're going to try to avoid negative exponents. So when we see we have this second problem, we're going to avoid all those negative exponents. So let's see what we have here in the first one. What I'm going to do here is I'm going to rewrite both of these expressions using rational exponents. So can you rewrite this piece as a power of x? Okay. Well, I have squared here. I have a cube root, so this is x to the 2/3 power. How about the second expression? How can you rewrite it as a power of x? Well, it's x to the first, the fourth root of it, excuse me. That means x to the 1/4 power. Those expressions are being multiplied. And we know that the rule for multiplying is that we add exponents. So this will be x to the 2/3 plus 1/4. This now just becomes a fraction problem. I know a least common denominator is 12. So I have x to the 8/12 plus 3/12. And therefore, this whole thing is x to the 11/12. And then you have to look at the instructions of the problem which you're given. I'm very happy with writing it as x to the 11/12 power. I don't think I'd want to write this as a radical, but if I was told that I needed to, this would be x to the 11th, its 12th root, which looks pretty nasty. But you just have to pay attention to the instructions. I think x to the 11/12 power is just fine and dandy. Last example here, and then we're done with this video. There's actually a couple ways you can proceed here. One way to proceed would be to take this negative 2/3 power and sprinkle it to all of the powers we see. That's one of the rules, one of the things we're allowed to do. But I actually think there's an easier way to do it. One way I like to do these things, let me erase the junk that I just put on the board here. I think an alternate way to do this is anytime I see parentheses and I see the same base in parentheses like these, I think it's easier to try to simplify those guys first. So let's go ahead and try to do that. I'll bring my work down here. I see x to the fourth over x to negative second power, and I know that when I do that, I'm supposed to subtract my exponents. 4 minus negative 2 is x to the sixth. Same deal here with the y's. I have y to the negative 6. Let me write some work over here. Negative 6. And I have y to the 1/3. Well, I'm supposed to subtract those. And this is a little bit messier, but I'll go ahead and subtract them. I need a common denominator. That's 18ths. Excuse me, that's thirds. So I'll have negative 18 thirds minus 1/3. Negative 19 thirds. Looks pretty nasty, but we'll see where it heads. Okay. And it's all being raised to negative 2/3 power. Okay. And now I know that this negative 2/3 will become part of both these exponents, and we multiply to do that. So I'm going to have x to the sixth times negative 2/3 times y to the negative 19 thirds. I'm making kind of a mess here. Negative 2/3. This is not the prettiest problem of all time. I'm running out of board space too. So simplifying a little bit, this is x to the negative 12 thirds. Wasn't that nice? That's going to make a negative 4. Times y to the, isn't this nasty? It will be positive though, 38 thirds. Okay? Because I'm running out of board space here, let's simplify a little bit here. I have a 4 here. In fact, it's a negative 4. Keep in mind that negative 4 means I'll have the fourth power, but it'll be in the denominator. So the final answer for this one, the final way to simplify it is I have y to the 38 thirds over x to the fourth. And that is done. It has no negative exponents. So these are getting a little tricky, but if you remember your laws of exponents and keep in mind with the rules, then you'll be in good shape.